In this lecture, we will talk about rules for significant figures, types of errors, and propagation of uncertainty. This is going to be Chapter 3 material. The value recorded for a measurement should use all the digits known with certainty, plus an additional estimated digit, which is considered uncertain. And the total number of digits used to express such measurement is called the number of significant figures. Let's take a look at the example below. How long does it take to travel 128 miles at 70.0 miles per hour? How many digits do you want in your answer? How accurately do you know the parameters? Our answer will depend on the amount of significant figures in given parameters. As you can see, 70 miles per hour is given with a decimal place, and this indicates the accuracy. So this number has 3 significant figures. If a 0 is given after the decimal point, it indicates the precision, the accuracy goes all the way to the right, and we say that this 0 is shown for a reason. It indicates the accuracy. By contrast, integers are exact, and exact numbers have unlimited number of significant figures. So our limiting term is actually 70.0 miles per hour. Looking at this number, we can only report our answer with 3 significant figures. So D is the correct answer in this case. And now let's review rules for significant figures. Significant figures is the minimum number of digits needed to write a given value in scientific notation, without a loss in accuracy. We always report digits with minimum uncertainty plus minus 1. For very large numbers, it's always best to use scientific notation. For example, a number 23,500 is ambiguous. I can say that this number contains 3, 4, or 5 significant figures, and I don't know anything about this number, so I cannot say with certainty how many significant figures will I need in my answer if I use this number in calculations. So it's better to write such numbers in scientific notation, because this decimal point is not shown. This may or may not be significant. So this number can have 3, 4, or 5 sig figs. But if I show it in the scientific notation, then I can certainly show how many significant figures I have. So 2.35 times 10 to the 4th has 3 significant figures, or I can add one more 0 and it would have 4 significant figures, and so on. So the general rules for significant figures are the following. Any non-zero number is always significant. Zeros are significant when they are either in the middle of a number, so captured zeros, or they're at the end of the number on the right side of the decimal point. For example, a number 54.07, this captured zero is significant, so there are 4 significant figures in this number. And if there's a decimal point and there are zeros after the decimal point, then these zeros are shown for a reason. They show accuracy and they are definitely significant. So this number has 5 sig figs. There's always some uncertainty in the last digit for any measurement. If we use analytical balances, for example, the last digit may slightly fluctuate due to the evaporation or condensation going on, and we typically think that this last digit is uncertain. If we take a look at the picture and try to read the percent transmittance, so we can see the marks here and the numbers corresponding to the marks on the scale. These are going to be our certain digits, but then the last digit is going to be my guesstimate, so digit that I need to read kind of between the marks here. So I would interpolate the last digit to 1/10 of the distance between the marks. So what is the percent transmittance on the above scale? So we can definitely say that the percent transmittance is 58, this digits known with certainty, and then we need to guesstimate the last digit. Which answer would you pick? And actually, in this case, any answer would be a correct answer because it's really hard to read on this scale, and the last digit is really a guesstimate. It's definitely an uncertain digit, so any numbers from 58.1 to 58.5 could be the right answer. It really depends on the person who reads the scale, maybe the angle or the other conditions, but any of these answers would be considered the correct answer. For the addition and subtraction, we look at the number of decimal places in the limiting term. So the general rule for addition and subtraction is that the result cannot have more digits after the decimal point than any of the original numbers. For example, if we take a look at my last example here, you can see my limiting term 35.453 has 3 decimals. So my answer basically cannot have higher precision than any of the numbers I use in calculations, so therefore the answer must have 3 decimals. If we take a look at this example on the slide, you can see that my limiting term, which is 35.453, has only 3 decimals. My answer cannot be more accurate or more precise than any of the numbers I'm using in the calculation. So the answer must have only 3 decimals. The number of significant figures in the answer may exceed or be less than in the original numbers. If the number does not have the same number of sig figs, then we are limited by the least certain one. Let's take a look at the second example now. So the number of significant figures in my answer is more than in my original numbers. But again, for addition and subtraction, we basically look at the number of decimal places. So since both of the numbers have 3 decimals, then my answer will have 3 decimals as well. If we take a look at my next example here, the answer has less significant figures than my numbers that I'm using in calculation. But again, I'm limited to the number of decimal places, and since my numbers, both of these numbers have 3 decimals, then I must report my answer with 3 decimal places. Otherwise, it'll be more accurate than my numbers that I'm using for the calculation. Therefore, the answer is 0.037 times 10 to the negative 4th. And remember, when you subtract or add exponents, you need to express all numbers with the same exponent and align all numbers with respect to the decimal point. We can put this number into the scientific notation, and in this case it's going to be 3.7 times 10 to the negative 6. And sometimes we need to round off our answer depending on how many significant figures we should report in the answer. So when carrying out arithmetic operations, it's nice to carry the extra digits through the calculation and round off to the correct number of significant digits at the end. So round off the final answer. Look at all of the numbers beyond the last significant figure. If the number is more than 5, then we round up. Round last significant figure up 1. If the number is less than 5, then round down. Then round last significant figure down 1. If it's exactly 5, then round to the closest even digit. How many significant figures in the answer to the problem on the right? So let's take a look at the answer, 0.014 times 10 to the negative 4th. So if you remember, leading zeros are not significant. Why? Because they may come and go when we use a scientific notation. So basically, these leading zeros are not significant. And this is because if I put this number into the scientific notation, 1.4, they disappear, times 10 to the negative 6. because I moved my decimal place 2 times to the right. So this answer has only 2 significant figures. Now let's talk about multiplication and division. For multiplication and division, the result cannot have more significant figures than any of the original numbers. So basically the total number of sig figs in the numbers that we use matter. For example, 5.730 times 10 to the negative 6 multiplied by 3.2. Let's look at the number of sig figs in each of the numbers that I'm using. The first one contains 4 sig figs. All the zeros shown after the decimal point are significant, and my second number contains only 2 sig figs. So which means that my answer should have only 2 significant figures, otherwise it will be more precise than 3.2. So we should round this number, the answer, to 1.8 times 10 to the negative 5th. In my second example, both of the numbers, so ignore the exponent. Exponent does not influence the number of significant figures. So we only look at the number, 3.00, 5.43. Both of the numbers have 3 significant figures. And therefore my answer should have 3 sig figs. 1.63 times 10 to the negative 27th. Next example, 25.96 divided by 3.141578. So my first number has 4 sig figs. Second number contains 1, 2, 3, 4, 5, 6, 7 sig figs. My answer cannot be more precise than any of the numbers that I'm using, and therefore I need to report 4 significant figures in my answer, so 8.263. And what about very large numbers, like 327,000 multiplied by 3.245? So again, a large number such as 327,000 is an ambiguous number. It's best to use scientific notation for such numbers because we don't know if these zeros are significant or not. We don't know anything about this measurement. So we can say that there may be 3 sig figs in this number, or maybe there are 4, 5, or 6 significant figures. Since we don't know anything about this number, we don't know how many sig figs really in this number, it's not shown in the scientific notation, so we would limit our answer to the minimum number of significant figures. So I would say there are 3 sig figs in this number, and the next number contains 4 sig figs, but again we need to report only 3 since one of the numbers has only 3 sig figs. So we would round our answer and use a scientific notation. So the correct answer would be 1.06 times 10 to the 6. How many significant figures in the answer to the problem on the right? First of all, let's calculate the answer. The answer is 16.31628 times 10 to the negative 28. So how many significant figures should we use in this case? Let's count the number of significant figures in each of the numbers. This number has 3 sig figs. And this number has 6 sig figs. It means that we can only report 3 significant digits for our answer. Now let's take a look at the functions, logarithms and anti-logarithms. For logarithms, let's consider formula a is equal to the logarithm of n. Given n, how many sig figs we should report for an a? A logarithm is composed of a characteristic and a mantissa. The characteristic is the integer part. This is the integer part, and this is mantissa part, which is simply a decimal part. The number of digits in the mantissa of logarithm should equal the number of significant figures in A. So if we are given an n, which is the number under the logarithm, and we know that it has 3 significant figures, then the A will have 3 decimals. In the conversion of a logarithm into its anti-logarithm, which is an opposite function, 10 to the x, usually on your calculators, or 10 to the a in our case, corresponding to the formula above, the number of significant figures in the anti-logarithm should equal the number of digits in the mantissa. For example, anti-logarithm of number 4.37 is basically the same as 10 to the 4.37. So how many sig figs in this number? There are technically 3 significant figures, but again, we'll look at the characteristic and mantissa. So we care about how many decimals this number has. So since it has 2 decimal places, our answer will have 2 significant figures, 2.3 times 10 to the 4th. So to simplify this, when you calculate a logarithm of something, let's say log of 3.2, look at the number of sig figs in the number under the logarithm. Your answer should have the same number of decimals, 0.51. 2 decimals corresponding to 2 significant figures in the number under the log. When you're working with anti-logarithm and you use 10 to the x function, look at the number of decimal places in the power. Your answer will have the same number of significant figures as the number of decimals, 2.3 times 10 to the 4th. So let's summarize all the rules that we've discussed so far. For addition and subtraction, result contains the least number of decimals. So we care about decimals. We have two numbers, 5.167 plus 2.1. Look at the number with the least amount of decimals. This is your limiting factor, so your answer contains the same number of decimals, so 7.3. For multiplication and division, we care about total number of significant figures. Result contains the least number of sig figs. So if we multiply these two numbers now, the first one has 4 sig figs, the second number, 2.1, has 2 sig figs. The answer should contain 2 sig figs, so 11 point. This is our answer. For logarithm, sig figs in the number under the logarithm corresponds to the number of decimals in the result. So if I want to take the logarithm of 4.37 times 10 to the third. So again, the power has nothing to do with the number of sig figs, we just ignore it. Just make sure you enter it on your calculator. But look at the number, 4.37. It contains 3 significant figures. So my answer will have 3 decimals. The answer is 3.640. 3 decimals corresponds to 3 significant figures in the number under the logarithm. For exponential function or anti-logarithm, the number of decimals in the initial number, in the power basically, corresponds to the significant figures in the result. So 10 to the 4.37, my power contains 2 decimals. It means that my answer will have 2 significant figures. So 2.3 times 10 to the 4th. Let's take a look at the example. Remember that pH scale is actually a logarithmic scale, and pH is equal to the negative logarithm of the molar concentration of the H+ cations in solution. So how many significant figures does the molar concentration of H+ value have? The pH reported here is 7.030. To calculate the H+ concentration, we need to take the anti-logarithm of this value. So basically 10 to the negative x function, or 10 to the negative pH. H plus concentration is equal to the 10 to the negative pH. Since we are working with the anti-logarithm, we care about the number of decimals in the power. So 3 decimals, which means that we will need to round our answer to the 3 significant figures. So the concentration of the H plus ions is 9.33 times 10 to the negative 8. We rounded this number to 3 sig figs. If the hydrogen ion concentration is 1.058 times 10 to the negative 7th, and this is molar concentration, then what is the pH to the correct number of significant figures? To calculate the pH, we need to take the negative log of the concentration. Now count the number of significant figures in the number under the logarithm. It has 4 significant figures. So these 4 significant figures will correspond to the number of decimals in our answer. So we need 4 decimals in the answer, and looks like the answer that we want is C. Let's specify that this is the number of decimals in our answer. Now let's take a look at this picture and let's try to read the absorbance value. How would we report this value? We know that we need to report all the digits known with certainty plus 1 uncertain digit. But what is our uncertainty here? If you take a look at the scale here at the bottom of this picture for absorbance, we can see that we know the 10th and the 100th place with certainty. So the smallest scale division corresponds to the 100th place. So our digits known with certainty are 0.2, and then we count 1, 2, and 3. So 2, 3 are certain digits. Plus we need to report one uncertain digit. If you take a look at the picture here, the readout line, or the needle, is 1,000 units wide. So we would guesstimate our last thousandths place. We could say that the absorbance value is 0.234, and since our readout line is 2,000 units wide, we can say that this answer is only certain to plus or minus 0.002. Plus, the absorbance scale is nonlinear scale, and so readout is even more complicated. So every measurement has some uncertainty, and conclusions can be expressed with a high or a low degree of confidence, but never with complete certainty. Now we're going to talk about the types of error. Experimental error is classified as systematic, random, or blunder. Systematic error, or also called determinate error, comes from a flaw in equipment or the design of an experiment. This is a repeatable error and can be determined and corrected. For example, if we read the meniscus level in volumetric flask incorrectly. Random error, also called indeterminate error, arises from uncontrolled or uncontrollable variables in the measurement. Limitations in our ability to measure some physical quantity or on small changes in the quantity itself. This error has equal chance of being positive or negative. Random error is always present and cannot be corrected. For example, weighing a sample without tearing or zeroing the scale is an example of what type of error? Determinate or indeterminate? This type of error would be determinate error because it can be corrected. So we can tear or zero out the scale and remeasure, reweigh the sample. The third type of error is called blunders. or gross errors, and these are extreme instances of random or systematic error. Blunders are pretty much unrecoverable errors due to some mistakes, maybe in procedure or instrument. For example, if I do a titration and significantly over-titrate my sample and completely miss the endpoint of the titration, this would be a blunder or gross error. Now let's talk a little bit about precision and accuracy. Precision describes the reproducibility of a result. If you repeat the experiment, maybe measure a quantity several times, and the values agree closely with one another, then your measurement is precise. Accuracy shows how close the measured value is to the true value. For example, if you have a known standard and it's available, the accuracy shows how close you are to the known value. A measurement might be reproducible but wrong. And good agreement among several methods gives us confidence that the results are true. So if we take a look at the picture here, as you can see, Cheryl is neither precise nor accurate. Cynthia is more precise and a little bit more accurate because the results are close to the target value. Carmen is very precise and accurate, close to the true value. And Chastity is precise because all of the values are reproducible, they are pretty much the same, but inaccurate in terms of the true value, far from the true value. Every measurement has some uncertainty, and there are two types of uncertainties: absolute uncertainty and relative uncertainty. Absolute uncertainty expresses the margin of uncertainty associated with a measurement. For example, if I report my volume as 3.562 plus minus 0.003 milliliters, it means that the actual volume can be between 3.559 and 3.565 milliliters. Another way of showing this and showing the uncertainty in the parentheses. So this basically tells me that the last digit is certain to plus or minus 3. Relative uncertainty compares the absolute uncertainty with its associated measurement. Relative uncertainty is calculated as absolute uncertainty divided by the magnitude of measurement. So if we go back to the previous example, the absolute uncertainty was 0.003, and we divide this by the magnitude of measurement, 3.562. So the relative uncertainty is 8 times 10 to the negative 4th. We can also express a relative uncertainty as the percentage by taking the relative uncertainty and multiplying it by 100%. So in this case, we get a percent relative uncertainty. And again, if I use a previous example, so my absolute uncertainty was 0.003 divided by 3.562, and now I'm gonna express this as a percentage by multiplying by 100. So my percent relative uncertainty is 0.08%. The percent relative uncertainty is more important than absolute uncertainty. We can usually estimate or measure the random error associated with the measurement. In most experiments, it is necessary to perform arithmetic operations on numbers with uncertainties associated with them. So basically, we treat our random errors statistically. To do that, we use standard deviation of the mean, and confidence interval. So the uncertainty is expressed as standard deviation or confidence intervals. The uncertainty does not simply add or multiply along with the experimental numbers, and because some of the errors will be positive and others will be negative, there is some cancellation of the errors that is expected in every measurement. Suppose we want to perform some addition and or subtraction. So we have two numbers, and each of these numbers have some uncertainties. Both of these have experimental uncertainties, and these are shown as E1 and E2. So let's say I added this two numbers, 1.745 plus 3.160, and I obtained my final answer. But what is the uncertainty associated with this answer? For addition and subtraction, the uncertainty in the answer is obtained from the absolute uncertainties of the individual terms, according to the following formula. So if I plug in my experimental uncertainties here, 0.003 squared plus 0.002 squared, I get the answer as square root of 0.000013, and this is equal to 0.004. So the final answer is 4.905 plus minus 0.004. Now let's take a look at multiplication and division. For multiplication and division, first convert all uncertainties into percent relative uncertainties, and then calculate the uncertainty of the product according to the formula. So, to convert our uncertainties to the percent uncertainties, we take absolute uncertainty and divide that by magnitude of measurement, or basically divide that by the measured value. So 0.003 divided by 1.745, and then express this as percentage by multiplying by 100%. So here is my percent uncertainty for the first value, and I do the same for the second value. So I take my absolute uncertainty 0.002, divide by the measured value 3.160, and multiply by 100%. So now I have my percent uncertainties ready, and I plug them into the equation, which is similar to the equation for addition and subtraction, but now we use the percent uncertainties here. So once we calculate our answer, we get our percent uncertainty again. So this is a percent uncertainty. And if we want to convert these uncertainties to absolute uncertainty, we need to basically find this percentage of the answer. So we take this relative uncertainty multiplied by the answer, which we calculated, 5.514, and then get rid of the 100%. So basically divide by the 100%. This gives us absolute uncertainty of 0.01. So our answer is 5.51 plus minus 0.01. Notice that in this example, the answer shows only 2 decimals, not 3 decimals, because error is in the second decimal. Now let's take a look at other rules for propagation of uncertainty. Let's talk about anti-logarithms or exponential functions. Anti-log is really an exponent. So as you can see, here's the formula, the function that I'm using, 10 to the x. And my formula to the right shows how to calculate relative error. So if you remember, the absolute error in y divided by the value of y gives me the relative error. So I'm basically summarizing on the right here the meaning of this formula. So the relative error, which is just absolute error divided by the value, is equal to 2.303. So this number comes from the value of the natural log of 10. So if you take natural log of 10, you'll get 2.303. And then this number is multiplied by the absolute error in x. So this. Now let's take a look at the example. We are given the value of x, and we know the absolute error in x, 0.02 is our absolute error. So the answer is given. Let's take a look how we get to this answer. So first of all, I need to calculate my y, 10 to the negative 4.45. This gives me the following value, 3.548. I'm going to keep all my digits without rounding them, and then we'll decide how many sig figs I need in my answer. So 13 times 10 to the negative fifth. So how many sig figs should I report, and what is the uncertainty? Where is the uncertainty in y? Let's start by calculating the relative uncertainty or relative error, basically. So which is going to be our absolute error divided by the value of y. So I'm going to use my formula, 2.303, and multiply it by the absolute error in x, which we said was 0.02. So this gives me the following value, 0.04606. And again, this is the relative error. I want to know the absolute error in y. So to find that, basically solving for this error, I just need to multiply my value here, 0.04606, by the value of y, which I calculated by 3.54813 times 10 to the negative fifth. So now I get the following value for the absolute error in y, 0.1634, and has more significant digits here, times 10 to the negative fifth. But remember that we keep only one significant figure in absolute error. So I'm going to round it to one sig fig, 0.2 times 10 to the negative fifth. And I want to keep the same power, so instead of writing it in scientific notation, I'm keeping the same power, 10 to the negative fifth, because this is the absolute error that I'm going to be adding and subtracting from my value of y. So powers should be the same. So now let's write the final answer. Y is equal to 3.5 plus minus 0.2 times 10 to the negative fifth. Because my uncertainty is in the tenth place, so the absolute error is 0.2 times 10 to the negative fifth, I can only report one decimal, so the tenth place, for my value of y. So that is why I'm rounding the value of y to the two significant figures, so basically showing only the tenth place. Otherwise the y value will be incorrect. I cannot show any other decimals because the uncertainty is in my tenth place. Now let's take a look at the example for logarithmic functions. So here's the formula, or my function, y is equal to the log base 10 of x. And the formula that I'm using to calculate the absolute error is shown on the right. So basically, to calculate the absolute error, I will need to take the number 0.434 and multiply it by a relative error in x. So again, this ratio here, absolute error divided by the value of x, gives me the relative error. And see this on the right, I have kind of an explanation for this formula. So if we divide the relative error by a natural log of 10, in other words, if we just take 1 over natural log of 10 and calculate this value, we get the number 0.434. So then we take this number and multiply it by the relative error in x. So this is the meaning of the formula. So now let's take a look at the example. If we're given the x value, and we know the absolute uncertainty, let's calculate the answer for y. Let's think about how many significant figures we can report and what is the absolute error in y. So first of all, I'm going to plug in my value into the formula, take the logarithm of 725 times 10 to the negative fifth. This will give me the following value, negative 6. Again, I'm keeping more sig figs because I don't know where is my uncertainty yet, and I don't want to round my answer before I calculate the absolute error. 139966, and so on. Now let's calculate the absolute error for y using our formula, 0.434 multiplied by the relative error in x. So we're just going to take the absolute error in x, which is given here, 0.05, and divide that by the value of x, 7.25. This will give us the absolute error in y, which is going to be 0.003. Again, for absolute errors, we just keep one significant figure. So I rounded my answer to one sig fig. And as you can see, the uncertainty is going to be in the third decimal. It means that in my answer for y, I can only report 3 decimals. Third decimal. So now I can write my answer -6 point, and I'm gonna round to have 3 decimals, 140 plus minus 0.003. For a complete list of functions, take a look at the table 3.1 on page 62 of our book. It gives a nice summary of rules for propagation of uncertainty for various functions, and it gives all the formulas for uncertainties. So we'll take a look at one more example, and this is going to be from Sapling Learning Homework, and this is for the function x to the power of a. So here's our x value, 8.47 plus minus 0.06 to the power of 1/3. On the right, I have the formula for percent uncertainty. So we will need to start with the percent uncertainty first and then calculate the absolute uncertainty. The formula is pretty easy. We just need to use the power a and multiply it by percent uncertainty in x. So the percent uncertainty is pretty much a relative uncertainty, which is going to be the absolute uncertainty of x divided by the value of x and then multiplied by 100%. So let's calculate the value of y first. So we're just going to take 8.47 to the power of 1/3. And this will give us the following answer, 2.03843. Again, I'm keeping more sig figs. I don't know where is my uncertainty yet. I think this is enough. It has more sig figs in the answer anyway. Now let's start with the formula. Percent relative uncertainty in y is equal to the power a is 1/3 multiplied by the percent relative uncertainty in x. So as you can see, the absolute uncertainty is in x is given in the parentheses. So 0.06 divided by the value of x, 8.47, and multiplied by 100. We basically express percent uncertainties because we don't want to deal with very small numbers. So they just give us more convenient numbers, I guess, for percent errors. So this is equal to 0.2%. Again, and this is the percent relative uncertainty. I also want to know the absolute uncertainty because in many cases we show absolute uncertainty rather than percent uncertainties. So let's calculate that. First, let's find out relative uncertainty. Get rid of the percentages. So the relative uncertainty is going to be equal to the percent uncertainty in y divided by 100%. This is equal to 0.002. And now I can calculate absolute uncertainty by multiplying my relative uncertainty by the value of x. Remember that relative uncertainty is also equal to the absolute uncertainty divided by the value of y. So to calculate my absolute uncertainty, I'm going to take relative uncertainty, 0.002, and multiply it by y value, 2.038423. Now this gives me the following value. I'm rounding to one significant digit, 0.005. So my uncertainty is going to be in 1000ths place, and I can only keep 3 decimals in my answer. So y is equal to 2.038 plus minus 0.005. In the next lecture, we will talk about error propagation. Please continue reading our book, chapters 2 and 3, and keep working on sapling assignments.